last class we started discussions on state space representation of discrete systems. Now, if you remember, we took up a system like this. Bz by Az is the transfer function. We broke it up into two parts, the numerator and the denominator, they were segregated. It can be either this way or this way. Okay. We also wrote the discrete domain equations for these intermediate variables either in this form or in this form, and the output yn we wrote in terms of this intermediate variable Vn in this form. We selected some functions, time domain functions like this. So, we will continue from here. So, the discrete functions that we defined, S1n was Vn minus n, S2n is Vn minus n plus 1 and so on. Snn was Vn minus 1. Okay. Therefore, we can write Sn plus 1 equal to Vn minus n plus 1, which is nothing but S2n. Similarly, S2n plus 1 will be equal to S3n and so on. Okay. Only the last one, Snn plus 1 will become Vn, which is, see, Vn minus 1 plus 1. So, that will become Vn, which we derived as xn minus a1 Vn minus 1 and so on. So, I can write this as xn minus a1 into Sn n minus a2 into Sn minus 1 n minus an S1 n. Correct me if I am wrong. Is it all right? Now, therefore, we can get all these S1 n plus 1, S2 n plus 1 and so on, Sn n plus 1. Okay. You watch it here, there is a matrix which is a diagonal in this subdiagonal form, and S1n, S2n and Snn. Last one will be minus, it ends here, these are all zeros, an minus an minus 1 and so on up to a1 plus, I can write 0 0 0 0 only last one into xn. Okay. This is a very familiar form that you have studied in control systems, okay, in the continuous domain, and yn is, what was yn? If you remember, B0 into Vn, B1 into Vn minus 1, and all these Vn's are basically the states S1, S2. So, I can write this as B0 Vn plus B1 Vn minus 1, this summation plus Bm Vn minus m. I need not put a bracket, this is all sum. Anyway, I can write this as B0 into Vn was xn minus a1 v n minus 1, okay, minus a2 v n minus 2 and so on up to minus a n v n minus n. Okay. Then this plus b1 into this, b2 into the next term and so on. So, plus b1 into v n minus 1 plus b2 into v n minus 2 and so on up to the last term bm v n minus m. Okay. Let me change the pen. Is that all right? So, you can club the terms v n minus 1 together, the coefficients of this, minus a 1 b 0 plus b 1. So, it will look like this. If you permit me to put them together, it will be b 1 minus b 0 into a 1 into v n plus b 2 minus b 0 into a 2 into v n minus 1 and so on. You can write b m minus b 0 into a m v n minus m minus b 0 a m minus 1 v n minus m minus 1 and so on up to minus b 0 a n v n minus n. Okay. It will come as a difference of these two terms only up to mth term, all right. After that it will be a single coefficient, because the numerator is of mth order, denominator is of higher order nth order. So, I can write this as minus b 0 a n, then this is a row matrix, okay. b 1 minus b 0 a 1 whole thing into S 1 n into S 2 n up to S n n plus b 0 x n. Any slip anywhere? Plus b 0 x n, this term was missed out. Okay. It was b 0 into x n, the first term. So, when we clubbed them, that was dropped out by slip. Okay. Is this all right? It is not correct? Okay. Fine. Let us see what is it. Minus b 0 a n, b 0 a n into v n minus n. What is it? That is S 1. So, it should have been reversed. Okay. It should have been the other way. It will start with, no, this is a row only. The first element is previous step, b 1 minus b of n minus 1 v we are replacing v n, thank you, v n minus 1, n minus 2 and so on. Okay. Otherwise, this is all right. Thank you very much. So, I can write this as in a compact form, all right, a into S n, where this is a vector of all the s, S1, S2, S3 and so on, okay, plus b into x n, where b is basically this, all right, that column that I got here, B is this, A is this, okay, and y n is equal to C into S n plus D into x n. So, D is this single element, okay, because this is y, this is y n, all right, and C is this row. So, we get what would be the solution for this? Suppose it is initially relaxed, we will take up that. If it is not relaxed, then we will have to find out what is its initial condition, initial state. This S we call the state of the system, it is the general health of the system. It can be velocity, acceleration, you can have any parameter of the system, any variable of the system as a state. Okay. Now, the choice of states is not unique, it can be anything, any linear combination of the states that you take, I can choose as a different set of states. Okay. So, under some choice, suppose we have selected the states, S1 I can write as A into S naught plus B into, okay, S2 will be A into S1 plus B into X1, and S1 is this much. If I substitute for S1 this quantity, I will get A into A, S squared S naught plus this whole thing multiplied by A, AB into X naught plus B into X1. Is that all right? That means the effect of the input at the previous instant will be felt even at the present instant, all right. It will leave a trail. So, you have like this, and y n output will be C into S naught. If I want to compute it for naught plus D into X naught, okay. This is for n is equal to 0, okay. And if I compute for other values of n, y n, all right, I will have to keep on taking S1, S2 and all the terms. So, C A n S naught plus C sigma A n minus 1 minus m B x k. I should write k, okay, m for n greater than 0 plus the d term is left out, d x n. This you can see by substitutions. I have not written S at other higher values S n. What will be this? You will get A squared, A cubed, A 4 and so on, A to the power n, all right. Similarly, A to the power n minus 1 and so on, okay. B will not be squared any time, B will appear as it is A which will come start appearing here and next terms and so on. So, these all these can be put in a summation form, and C times x, so C times S, so C times that at S n whatever is this, if I multiply by C, so that summation term, leaving aside the 0th term, so it will be like this. Okay. So, one may write for n greater than 0, it will be, this is the general term, this is y n, for n greater than 0, it will be finally C a to the power n minus 1. If you have an initially relaxed condition, that means initially S0 is 0, S0 is 0, alright. That means in an electrical circuit there is no charge, there is no stored magnetic field in the inductor and so on. If you have an initially relaxed condition, then S0 will be 0, everything will come to a steady state, alright, that will be a 0 state. So, this will be vanishing, it will start from the second term onward, B, okay, into delta 0 plus C, that is equal to C a n minus 1 B. Suppose basically what I am trying to find out is initially relaxed and I give an impulse, alright, that is at delta equal to delta n, that is at n is equal to 0, I give an impulse. What is the response? Okay. Otherwise there is no response. If it is initially relaxed, let it relax, it is not, you give an input. So, normally you test it with an impulse signal. So, if I give an impulse input, this will be the kind of response. Okay. So, this I can call as Hn. Normally the impulse response is denoted as Hn of the system. Okay. Now, from the difference equation, we can write a state equation, alright, that is what we started off, is it not? If you remember the very first day, we could write the difference equation, this is the difference equation, it could have been either in this form or in the other form, alright, Bz by Az is given, you can always write the difference equation form, that is they all appear in terms of small a's and small b's, these are the difference equation constants, is it not? Now, from the state space equation, can you get the difference equation? So, now I will just take up we will take up an example. Given A as 0.5, 0.4, minus 0.2, 0.3, B as 1, 3, C as 2, 3 and D as 0.4. What will be the difference equation? Okay. Now, before that, before we start off, let us get back to the state equation once again. If we take Z transform of this, what do you get? Z into Sz, okay. This side will get A into Sz plus B into Xz. Sz is a vector because S1, S2 these are all vectors, elements of the vector. So, Zi minus A into Sz is equal to B into Xz. Do you all agree? Is this okay? Therefore, Sz is Zi minus A inverse into B into Xz. all right. And then we have yz. See, what was yn? C into Sn plus d into xn. So, yz, mind you, these are not vectors. Finally, the matrix product S only will be the vector, others are all scalars. So, after taking the products, you will get only a scalar quantity. So, this will be C into Sz plus d into xz, okay. And what is Sz? This much. So, if I substitute C into Zi minus A inverse into B into xz plus d into xz. So, can I write like this? Okay. Therefore, y by x in the z domain, this is a transfer function, is C into Zi minus A whole inverse B plus d. Okay. Now, our aim is to obtain from this set of given matrices A, B, C, D, compute this. So, in the z domain you get the transfer function. Once you know the transfer function, you know the difference equation. So, let us compute this for this now. I hope this is all right. So, for the given problem, Zi minus A, so these terms will be all negated, subtracted from Zi. So, Zi minus A inverse will be, how much is it? Z minus 0.5 minus 0.4, this will be minus, this will be minus, this will be plus, this will be minus. So, this will be 0.2 and Z minus 0.3, is that all right, to the power minus 1. Okay. So, this comes out as, check if I have made any mistake, Z minus 0.03 and then minus 0.4 will become plus 0.4, this will become minus 0.2 and this will become Z minus 0.5 and that divided by this plus this. So, that gives me Z square 0.5 plus 0.8, so minus 0.8 and 0.5 and 0.3 and then 5 3s are 15 and 8, so plus 0.23. Correct me if I am wrong, is that all right? Okay. So, C into Zi minus A inverse B plus D turns out to be 2, 3, then you have Z minus 0.3, 0.4 minus 0.2, Z minus 0.5 into B, that is 1, 3, okay. Whole thing divided by Z square minus 0.8 Z plus 0.23 plus 0.4. Okay. If you simplify 2 into this plus 3 into this, whole thing into 1 plus 2 into this plus 3 into this, whole thing into 3, that will be the numerator. So, I write 2 into Z minus 0.3 minus 3 into 0.2, whole thing into 1 plus 2 into 0.4 plus 3 into Z minus 0.5, whole thing into 3 divided by Z square minus 0.8 Z plus 0.23 plus 0.4. So, 0.4 times this you can add in the numerator. So, finally, you get, if I add this 0.4 z square plus 11, see 2, 3 3s are 9. So, 9 plus 2 11 minus 0.4 into 0.8. So, minus 0.32. So, that gives me 10.68 z, and you let me know what final value you get here. I have got this much, I may be wrong, z square minus 0.8 z plus 0.23. Okay. So, divide throughout by z squared. So, that gives me 0.4 plus 10.68 z to the power minus 1 minus 3 point, this is minus, I am getting minus 3.058 z to the power minus 2 divided by 1 minus 0.8 z inverse plus 0.23 z to the power minus 2. Okay. So, the difference equation from here comes out as, this is equal to y by x, is it not, y by x. So, y multiplied by this will be x multiplied by this. So, y n minus 0.8 y n minus 1 plus 0.23 y n minus 2 is equal to 0.4 x n plus 10.68 y x n minus 1 minus 3.058 x n minus 2. Is that all right? So, this is the difference equation you get after taking Z transform and then breaking it up. Now, we shall take up the general case of filters. Okay. Sometime earlier probably I had mentioned, I do not recollect, about the types of filters that we have. In digital systems, we have two types of filters. We define them as per their impulse response, IIR and FIR. Okay. Before we go for the design structures, design and structure of filters, we will like to know the general properties of filters. See, Hz, suppose Hz is B0 plus B1 Z inverse. We will talk in terms of the transfer function, that would be very convenient. Divided by okay, and that is equal to Bz by Az. This is what we mentioned earlier. If Az is equal to 1, then it is having only the numerator polynomial. Okay. So, Hz is only Bz. So, this is known as finite impulse response filter. If I give an impulse, after some time the output becomes 0. So, it continues only up to a finite length. So, if say Yn is 1.2 xn, I have just taken an example, say n minus 1 minus 0.5 x n minus 2. If I consider an initially relaxed condition, and if we give an input xn is equal to delta n, that means what is x0? 1, x1 is 0, and afterwards all of them are 0, x2, x3 etc. are all zeros. So, what will be the output y0? It will be 1.2 xn. So, 1.2 into x0, which is 1.2. What will be y1? It will be 1.2 into x at 1 plus 0.8 into x at 0, which will be, this will be 0, but this will be 0.8. y2 will be similarly 1.2 into 0, 0.8 into 0 and minus 0.5 into 1. So, for such a filter, these coefficients are nothing but the sequence of impulse response 1.2, 0.8, minus 0.5. Okay. So, basically this will be the coefficients of the impulse response. That is what we have also seen. Hz, if it is given only in the numerator form, so Hz will be H0, H1, H2 and so on. So, Hz is H0 plus H1 Z inverse plus H2 Z to the minus 2. So, in the filter coefficients, that is the coefficients of Z to the minus 1, Z to the minus 2, you get the impulse response terms. Alright. These terms denote basically the response at different instants for an impulse input. Suppose we have, on the other hand, yn is equal to xn minus a1 yn minus 1 minus a2 yn minus 2 and so on. Okay. This means Az is not 1, it is finite, but Bz is 1, is it not? If Bz is 1, then only it will be, this is 1. So, x gets multiplied only by the numerator and y gets multiplied by the denominator, and then if we shift these terms to the other side, you get such an expression. Okay. So, here you will find, even if I give a delta input, x 0 is 1, x 1 equal to x 2, they are all zeros, etc. equal to 0, then what will be y 0? These are all initially 0, initially relaxed, so they are all 0 initially. So, it will be x 0, which is 1. What will be y 1? It will be x 1, which is 0, minus a 1 times y at 0, which is minus a 1 into 1, that is x 0. Y 2 similarly will be how much? This will be 0, this will be minus a 1 times y at the previous instant, which is minus a 1 minus a 2 into y n minus 2, which was at y 0, which is 1. So, it will be minus a, and minus will make it plus a 1 square minus a 2, and it will continue like this. You will find, because there was an output in the previous instant, so it will be affecting the present output. So, it will continue till an infinite time. So, this second type of filter, we call it an AR process, auto regressive process. Whenever you have a situation when Bz is 1 and Az is finite, we call it auto regressive process or AR process of order n. If there are, it continues up to nth term, then AR of order n. And the previous one, when Az is 1, Bz is finite, then that is known as moving average of order m. Okay. When both are present, then it is AR and MA, we call it ARMA of order n, AR is of order n, MA is of order m. So, ARMA means n and m. Okay. Now, in digital filter, AR or ARMA, we call them IIR filters. So long as there is an AR part, it will continue up to infinity, whether this part is 1 or some finite length, it is immaterial. Because of the presence of the denominator, there will be always an infinite sequence, and MA filters are known as FIR, only numerator is present. Now, what are the advantages of this? What are the advantages of this? That we will come to know very soon. Now, there are different types of filters. If I take in the discrete frequency domain, this is the gain. An ideal low pass filter is like this. A real filter cannot maintain such stringent requirements, it will be somewhat deviating from the ideal characteristics. All right, there will be a tolerance within which you will be restricting the filter gains, and the design specifications will be given in terms of tolerance and other parameters like cutoff frequency and so on. You have to design a filter. So this will be the type of a low pass filter. Similarly, for a high pass filter, ideal high pass filter, an ideal high pass filter will be like this, and again here I will consider this also as a high pass filter. It is not an ideal one, but this is also an ideal high pass filter. Similarly, a band pass filter will be like this, and a band reject filter will be like this. It all depends on the thickness of this band, that how sharp this change is taking place. We term them as notch filter or inverted notch filter. Now, let us see. So far we are not really discussing about the phase, we will discuss in details at a later stage. Just one characteristic I would like to mention here. In a continuous system, suppose you are having an input like this. If you want a faithful reproduction of this as an output, obviously the system will not respond immediately. System cannot respond immediately. So there can be a delay, but after that I want the same output. That means I want yt to be x shifted by some time tau. If I take the Laplace transform, if it is a linear system, then x s into e to the power minus s tau. This we studied earlier in signals. So e to the power minus s tau will be the transfer function of the system in the continuous domain. What will be the phase characteristics of this? What is the Bode plot? What is the Bode plot for this gain plot? E to the power minus st, if I put s equal to j omega, so it is magnitude is always 1. Okay. If you take 20 log of 1, it is always 0. So Bode plot against frequency is always 0 dB. Okay. What about phase? E to the power minus j omega t. So omega t is the phase. So with respect to frequency, it will be negative minus omega t. So phase is s equal to j omega we are putting. So it is e to the power minus j omega t, that means the phase is omega into t, and omega is 2 pi f. So it is basically in terms of f, it is having a slope of 2 pi into t, this is a slope. Okay. So, you get a linear characteristics. That means, if I have a filter ideally of gain 1 and a linear phase characteristics, then I will have an exact reproduction of the signal, okay, with some delay, constant delay. So, a linear characteristic is very important. For example, when we transmit speech frequencies, speech signals, for different frequencies, if the gain is varying, if it is a filter, say a low pass filter like this, the gain is constant if my frequency is limited to this band, and if I can maintain the gain more or less constant, and I have to design a filter where phase is linearly changing with frequency, then only my voice will be faithfully represented, otherwise there will be distortion. Now, this is known as linear phase characteristics. Okay. Now, we will see how to achieve linear phase very soon. Now, let us again study the characteristics of filter functions from the location of poles and zeros. All right. Let us take first case when there are only zeros. That means Hz is having only Bz. All right. Let us take a very simple function, say 1 minus 0.5 Z inverse. All right. That means basically Z is equal to 0.5. Let us draw the unit circle. Z is equal to 0.5. Is that okay? So, h e to the power j omega, this is a z plane, complex z plane, this magnitude is unity, okay. This is a unity circle. Then h e to the power j omega will be how much? 1 minus 0.5 e to the power minus j omega, okay. So, h magnitude squared, I am not putting e to the power j omega every time in the argument, h square will be 1 minus 0.5 cosine omega whole thing squared plus 0.5 sine omega squared, correct me if I am wrong. So, that gives me 1 plus 0.25, 0.5 squared cos squared omega sin squared omega. So, 1.25 and then minus 2 into 0.5, so 1 into cosine omega. All right. When is it minimum? When is it minimum? When cos omega is maximum, that is at omega equal to 0. At omega equal to 0, h magnitude is minimum. Is that okay? So, that is equal to 0.5. 0.25 under root, this is h squared. So, 1.25 minus 1 under root of that. So, that becomes 0.5. And when is it maximum? When is it maximum? When this becomes negative. So, this will become 2.25. So, h maximum is under root of 2.25, that is 1.5. Okay. At what frequency? When this becomes negative, so omega equal to pi. Okay. So, let us see what it looks like. It starts from 0.5 and something like this. I am not making an exact sketch. 1.5. Is that all right? and then basically in this you are putting z is equal to e to the power j omega, is it not? Z is equal to e to the power j omega means you are going along this, you are taking omega at different points on this circle. So, that is what it is, e to the power j omega, omega is this, alright, this angle. When it is 2 pi, it is making a full circle, magnitude is 1, it is 1 into e to the power minus j omega. This is the substitution that we are making for z inverse. So, I am going along this. How much is this distance? I will put a 0 here because it is in the numerator, to be more precise, the root is shown as a 0. So, if I go along this, how much is this distance? That is given by this Bz, is it not? So, I am going along this. When is this distance minimum? Here. When is it maximum? When it is coming to this side, when it is pi. Again it is making 2 pi, so it is coming down. So, it will be maximum at pi, and then again it will be just mirror image 2 pi, and it repeats, sorry, it is like this. Okay. So, is it a low pass filter or a high pass filter? It is a high pass filter. Now, we will talk about only the frequency range up to pi, because it will be a replica of that. All our filter functions should be restricted to pi only, 0 to pi. If you remember that Shannon's criteria that we followed, all filter must be with a band limited signals. Next, suppose we have it as, okay, let us take another function h2z equal to 1 minus z inverse. What is it? 1 minus z inverse, how much is h squared? 1 minus cosine omega squared plus sin squared omega, that gives me 2 minus 2 cosine omega. Okay. So, what is it like? Is equal to 2 into 1 minus cos omega, and what is 1 minus cos omega? 2 sin squared omega by 2. So, 4 sin squared omega by 2. So, h is square root of this, so twice sine of omega by 2. Okay. When omega is equal to pi, this becomes pi by 2, so it becomes 2, and when omega is 0, it is 0. So, when omega is pi, it starts from here, it is a sine squared function. It is a sine function, sorry, sine squared is this, it is a sine function omega by 2. So, it is like this, alright. So, is it a low pass or high pass? It is also high pass. So, if the 0 is here or here, somewhere in the on the real axis here, it will be seen, see, as you vary omega, this distance becomes minimum when it is exactly at this point. So, at omega equal to 0, it is minimum. In case the 0 is on this, then it becomes 0, it starts from 0. If it is a little inside, then it starts from a non-zero value, but in any case it reaches maximum at omega equal to pi. Okay. Omega equal to pi means here, then the distance is maximum. From here the distance is so much, at any other location it is maximum at this point. Okay. So, this is a high pass filter. Next, let us take up a pair of roots. suppose we have two zeros here. Okay. We take this distance as r, it can be anywhere inside or on this or maybe outside. So, in general let the distance be r, alright. So, r into e to the power j theta, r into e to the power minus j theta, these are the two roots. So, the polynomial h z will be 1 minus r e to the power minus j theta into z inverse into 1 minus r e to the power plus j theta z inverse. Is that all right? So, that after multiplication gives me 1 minus 2 r. If you take out the real parts, okay, imaginary parts will get cancelled, you will find 2 r cosine theta, let me call it r1. We may take r1 is inside, we will take r2 when it is outside. Okay. So, 2 r1 cos theta z inverse plus r1 square z to the power minus 2. Okay. Correct me if I am wrong. Now, suppose r is equal to 1, r is equal to 1, then you get 1 minus 2 cosine theta z inverse plus z to the power minus 2 as a function, all right. So, how much is h magnitude squared? 1 minus twice cos theta e to the power minus j omega plus e to the power minus j 2 omega, this magnitude squared. Okay. Is that all right? How much does it come to? 1 minus, we have already got this, 2 cos theta cosine omega, all right, plus r1 square is known, cosine 2 omega squared. That is all. Is that all? Plus twice r1 sin r1 is 1 cos theta twice cos theta sin omega, okay, sin omega, and is it minus or plus? Any one of them will be minus, okay, and then sin 2 omega, whole square. Is it okay? So, here you will find, if you simplify this, okay, I leave it to you. If you simplify this and then put different values of omega, you will find here you have got the zeros, you are varying omega like this. Now, at this point one of the factors is becoming very less, here it is very small, minimum, somewhere around theta you will find this value is minimum, again it starts increasing, all right. So, it starts from some finite value, it reaches a minimum here and again it goes up. At omega equal to theta approximately, you get a filter like this. Thank you. So, if I now keep on shifting this along this line, this pair, I maintains the same theta, but I change the value of R1. If I put it on this, then it will be 0. If it is inside, it will be non-zero. Again, if it is here, it will be non-zero. Is it not? So, it will become 0 for, it will touch like this, R is equal to 1. Okay. Now, you will find whether you bring it inside or outside, the magnitude will remain identical. It will touch a minimum and then again it will start increasing, but the nature is identical. So, for the same identical nature of functions, you can have two possible locations of zeros, either it may be inside or it may be outside, having the same angle theta. Okay. Minimum takes place at theta. So, there comes the question of phase. What about the phase? How do you identify? I mean, there is an ambiguity. If you give only the gain plot, it can be a 0 here or it can be a 0 here. All right. So, we will see very soon how the phase is affected by the position of zeros. The situation when the zeros are all inside the unit circle, we call it a minimum phase system. There are poles. So far we are considering only zeros, there are poles also, we will take up that in the next class. So, when we have a pole zero combination, the zeros need not be inside, zeros can be outside, the system performance is still stable. It is the poles which are to be necessarily inside the unit circle, but the zeros can be anywhere. So, we will take it up in the next class, we will have